For nearly a century, astronomers have known that the universe is not standing still. Space itself is expanding, carrying galaxies farther apart as cosmic time moves forward. This revolutionary discovery changed humanity's understanding of the cosmos and revealed that the universe is far more dynamic than anyone had imagined. One of the key pieces of evidence for this expansion comes from a phenomenon known as redshift. As light travels across the expanding universe, its wavelength stretches, shifting toward the red end of the spectrum. By studying this effect in distant galaxies, scientists have been able to reconstruct the history of cosmic expansion and uncover one of the greatest surprises in modern astronomy. Instead of slowing down under the influence of gravity, the expansion of the universe appears to be accelerating. Researchers attribute this acceleration to an unknown phenomenon called dark energy, a mysterious component believed to dominate the energy content of the cosmos. Alongside dark matter, which helps shape galaxies and large-scale structures, ordinary matter, the stars, planets, and everything visible to us, makes up only a small fraction of reality. This realization has transformed our understanding of existence. Everything we can directly observe represents only a thin layer of a much larger cosmic framework that remains largely invisible. As the universe continues to expand, galaxies that are not gravitationally bound to our local region drift farther away. Over immense periods of time, many of them will move beyond a cosmic boundary where their light can never again reach us. This process is already occurring. Although the universe may extend far beyond what we can observe, our view is limited by both the speed of light and the ongoing expansion of space. When astronomers observe a galaxy billions of light years away, they are seeing it as it existed billions of years ago. During the time that light traveled toward Earth, the universe continued expanding, meaning that galaxy is now much farther away than the distance its ancient light originally crossed. This creates an extraordinary cosmic perspective. Looking deeper into space means looking further into the past, yet the most distant regions are simultaneously moving beyond our ability to reach or interact with them. The observable universe is not a fixed window but a constantly changing one. Because space itself can expand faster than light can travel across vast distances, entire regions gradually slip beyond our cosmic horizon. This does not violate the laws of physics, since objects are not moving through space faster than light. Rather, the space between them is expanding. Nevertheless, the consequence is profound. Portions of the universe become permanently inaccessible, not because they disappear, but because information from them can no longer reach us. As a result, astronomy has become a race against cosmic time. Every photon arriving at our telescopes carries information from an era that may never be observable again. Each distant galaxy represents a fleeting opportunity to study a chapter of cosmic history before expansion places it forever beyond our reach. This urgency is one reason why increasingly powerful observatories are being developed. Scientists hope to capture the faintest and oldest signals in the universe before they fade from view. In many ways, the cosmos is not concealing its secrets, it is steadily carrying them farther away. At the same time, a new mystery has emerged from the deepest observations ever made. Modern instruments are revealing patterns that challenge long-standing assumptions about the universe. Among the most intriguing questions is the apparent absence of vast amounts of expected starlight. At first, the idea sounds impossible. Stars do not simply vanish without a trace. They evolve, explode, collapse, or slowly fade over enormous timescales. Yet some deep space observations have revealed discrepancies between predicted and observed amounts of stellar light in distant regions of the universe. Rather than suggesting that stars have disappeared, many scientists believe the issue may involve how light travels across cosmic distances. The missing signal could be related to extreme redshift, dust obscuration, limitations in observation techniques, or incomplete models of early galaxy formation. Even so, the scale of the discrepancy has attracted significant attention. Where is this missing luminosity? Has it been hidden behind cosmic dust? Has its energy been redistributed in ways not yet fully understood? Or does the mystery point toward gaps in our understanding of how the universe evolved during its earliest stages? To investigate these questions, astronomers rely on one of the most advanced scientific instruments ever built, the James Webb Space Telescope. Designed to observe the universe primarily in infrared light, Webb can detect signals that have traveled across billions of years of cosmic history. Its extraordinary sensitivity allows it to peer through clouds of dust and reveal structures that were previously invisible. Since beginning operations, Webb has transformed our view of the early universe. It has detected galaxies that appear more massive and developed than many theoretical models predicted. Instead of finding only small, primitive systems in the distant past, astronomers have observed surprisingly mature galaxies existing far earlier than expected. These discoveries have sparked intense discussion within the scientific community. While they do not overturn modern cosmology, they suggest that certain aspects of galaxy formation and cosmic evolution may be more complex than previously believed. As Webb continues exploring deeper regions of space, additional puzzles have emerged. In some observations, the distribution of faint galaxies and stellar light does not perfectly match theoretical predictions. Researchers have proposed several explanations, including observational limitations, variations in star formation efficiency, and uncertainties in current models. Yet the deeper scientists look, the more important the question becomes. Are we overlooking a significant portion of the universe's luminous history, or are we still learning how to correctly interpret the ancient light arriving from the edge of the observable cosmos? For now, the answer remains uncertain. What is clear is that every new observation is expanding not only our view of the universe but also our awareness of how much remains unknown. The deeper humanity looks into space, the more the cosmos reminds us that its greatest mysteries may still lie ahead. The possibility that a portion of the universe's luminous history remains hidden raises questions that reach far beyond astronomy. At the heart of the mystery lies a simple challenge. Light is the primary messenger through which we explore the cosmos. Every image of a galaxy, every measurement of a star, and every estimate of cosmic distance depends on photons traveling across unimaginable expanses of space. If some of that light is missing, altered, or misunderstood, then our picture of the universe may be incomplete. One explanation involves the nature of cosmic expansion itself. As light journeys through the universe, it is stretched by the expansion of space. Over billions of years, wavelengths can become so elongated that visible light shifts into the infrared and eventually into ranges that are increasingly difficult to detect. In this view, the missing luminosity may not have vanished at all. It may simply have been transformed into forms that challenge even our most advanced instruments. Another possibility involves cosmic dust. Vast clouds of microscopic particles drift between stars and galaxies, absorbing and scattering light. While modern observatories can peer through much of this material, some regions remain difficult to study. Hidden behind these enormous veils, countless stars may contribute less visible light than theoretical models predict. What appears to be a shortage of stars could instead be a limitation in our ability to see through the universe's natural barriers. Yet some researchers argue that the mystery may point toward deeper questions about the earliest generations of stars. The first stars formed during a period known as the Cosmic Dawn, when the universe emerged from darkness and began producing light for the first time. These ancient objects were likely very different from the stars we observe today. They may have burned hotter, lived shorter lives, and enriched space with the elements needed to create future generations of stars and planets. If these early stellar populations behaved differently than expected, then current models of galaxy evolution may require refinement. Even small changes in assumptions about how stars formed and evolved could dramatically alter estimates of the total amount of light produced throughout cosmic history. The challenge becomes even more fascinating when astronomers compare observations with computer simulations. Modern cosmological models attempt to recreate billions of years of cosmic evolution, beginning shortly after the Big Bang and extending to the present day. These simulations have become remarkably successful at reproducing large-scale structures such as galaxy clusters, cosmic filaments, and vast empty voids. However, matching the fine details of real observations remains difficult. Tiny variations in star formation, black hole activity, gas dynamics, and dark matter interactions can produce significant differences over cosmic timescales. As a result, some of the apparent discrepancy may arise not from missing stars, but from the immense complexity of modeling an evolving universe. Adding to the intrigue are discoveries that continue to challenge expectations. The James Webb Space Telescope has revealed galaxies that appear surprisingly bright and massive at extremely early epochs.